here is New Generation, New Power. It is our privilege to have 3 renowned masters being with us today to share their valuable thoughts and experience. They are 第一位要介绍的是我们中央研究院的朱敬一朱院士，也是新上任的国家科学委员会主委。The first master is academician Ji Zhu from Academia Sinica. He is also the newly appointed Minister of the National Science Council. 诸位请上台，谢谢。朱院士在学术界的领域呢是非常的惊人，包括29岁就取得美国密西根大学经济学博士，43岁就成为当时最年轻的中研院院士，92年荣获总统科学奖，53岁就成为中经院最年轻的董事长。除了在学术领域的非凡成就之外，他还是位功夫高手，打了33年的太极拳，可见呢他的功力呢是深不可测。那么朱院士也是一位非常关心学校教育的院士，从2007年开始，连续3年分别到北中南的高中上1个学期的社会科学课，是第一位走进高中校园，用深入浅出的方式引导刚从国中毕业的学子走入人文与社会科学世界的中研院院士。让我们再次掌声欢迎朱院士。第二位我们邀请到的是徐遐生徐院士。The second master is academician遐生徐 from Academia Sinica. 那徐院士的丰功伟业，那就真的是不用多说，只要 Google 一下就是一大串了。徐院士被公认是世界顶尖的天文物理学者之一，也是让人非常肃然起敬的一位学者。那徐院士的专长研究行星诞生，尤其是漩涡状星系的形成以及恒星形成等2大理论，获得学术界极高的尊崇。那徐院士同时也是罕见，同时获选为美国国家科学院院士、中央研究院院士以及美国国家艺术与科学院院士3项学术荣誉集于一身的学者。让我们再次以热烈掌声欢迎徐院士。第3位呢，我们是中央研究院的刘兆汉刘院士。The third master is academician 赵汉刘 from Academia Sinica. 刘院士是太空科学国际知名的科学家，在美国的时候任职于美国伊利诺大学香槟分校。那90年代回到台湾之后，除了领导台湾大型的太空计划之外，也投入全球变迁的研究。刘院士担任过中央大学校长以及中研院的副院长。温良恭俭让5个字最能精准地描述刘院士的人格特质。他做任何的事情一定都先想得周全，以后再走下一步，谋定而后动，目标确定，仔细规划，慢慢经营是他的不二法门。那这些原则呢，也运用在中大校务的推动、个人学术研究之上，也皆有所成。那刘院士经常勉励青年学子，不要只局限于自我的学门，更应该要广泛的涉猎，以实力来展现自信，并且以有容乃大，共勉之。那接下来要欢迎我们的主持人，我们今天非常荣幸请到国立台湾大学物理系的吴俊辉吴教授来担任这一场讲座的主持人。吴教授主要研究领域是现代宇宙论，那目前也参与多项现代宇宙学的计划，那包括欧洲太空总署的普朗克卫星计划、美国的 Maximum Mexico 计划以及国内的 FOPA 计划，是一位青年才俊，也是各位同学师法的对象。Now let's please welcome the moderator of the session, Professor Junhui Wu from the Department of Physics, National Taiwan University. I'll give the floor to Professor Wu. Welcome.
So it's really a great honor to have 3 academicians all sitting together here, talking to the young generation here face to face. So in the next about 1.5 hours, we are going to proceed in 2 parts. In the first part, we will take turns for the 3 academicians to share their personal experience and some words they want to tell you, and it will take about 15 to 20 minutes each, right? And then after they finish their storytelling, experience sharing, we will start a Q&A session for about 20 minutes. Okay, so The first one who is going to tell the story is Professor Zhu. As you know, he was the youngest academician of NYC at the age of 43, and currently he is the chairman of the National Science Council. And also in the introduction, we learned that he's an expert in Tai Chi. So behave well when you meet him next time. So let's welcome Professor Zhu and see what he wants to tell us. Okay. Thank you, Moderator Wu. Should I start? Sure. Yes. Okay. Good evening, young scientists and ladies and gentlemen. It's my honor to be here to talk on this Taiwan International Science Affair. I'm now, starting from today, the chairman of the National Science Council, so I am really honored to be here. I was told that I have about 15 to 20 minutes. I'm going to deliver two opinions of mine. I dare not say advice, but opinions and experience. The first thing is that I would suggest continuous, persistent, lifetime learning. I'm going to explain more. Second thing is that I would suggest that you get used to making mistakes and tasting the taste of failure. Okay. Okay, let me explain the first thing. Continuous and persistent learning. I am age 57 now. I got my PhD at the age of 29. So it's about half time of my lifetime. 29 is about half of 57. I would say that 95% of my knowledge today were attained after my PhD degree. So in the first 29 years, first 50% of my lifetime, I only got 5% of my current knowledge. So how would that be the case? I would say that perhaps most of our school education focused on general communication skills and some basic common social values. General communication skills, including language, including basic mathematics, arithmetic. So you pay $100, buy something 36, you know that you should get 64 in return. This is communication skills. We also need to learn some basic fundamental social values. We should respect different opinions. We should learn something about democracy, freedom, speech. We should pay attention to the other people when they talk. Those social values, even including when your parents are angry. Okay? At that time you should obey so that you can get more money next week. This kind of values, this kind of social norms is something to learn, especially in the first period of schooling age. But the bad thing is that when you get to college, get your master or even PhD degree, what you learn is really narrow, or becoming really narrow. Let me give you an example. What Professor Robert Hutchins, who was University of Chicago president, some kind of people say that he's the father of general education. He said that in the age of 1930, when a history professor of the history department gave a baby or delivering, it's easy to find a replacement, say for 4 weeks or 3 weeks. But in the age of 1950 or 60, it's becoming very, very difficult because most history professor has a very narrow, specialized area. So some professors specialize in the labor relations history of the Detroit area from the year of 1955 to 56. So when that professor give a baby, there's no way you can find a replacement. So it's getting more and more difficult. That's the fundamental fact of a science area is science
science era that we divide things in a more and more refined way and focus in a very narrow area and concentrate, focus, and jump in that you get some development. So in general, I guess you would agree that most of the professors, or when you get your PhD, are actually, you know many things very little, but you know few things very much. That's the case. So that's what I got at the age of 29. I learned very few things very much, but know other things not too much. So I would suggest that you continue your learning, even if you get your PhD, even if you get your professor, get your tenure. In the past 27 years of research, I keep that in my mind. Even after I was promoted to professor, I sit in the School of Law to get all the law courses. So in the past, I published in areas including taxation, demography, evolutionary biology, philosophy, legal theory, urban studies. I did a lot of things. I can do this, I would say, mainly because I keep on learning. What's the advantage of broad learning and continuous learning? Robert Hutchins also provided an answer. He said in this modern world, because of the refined area and the narrow focus, the centrifugal force of our society is more and more serious. So everybody doesn't know what other professors are doing. In that case, it's difficult to communicate, not to mention appreciate other people's achievement. So that makes your life tougher, okay? If you're a history professor, you don't know not very much about astronomy, it makes the communication difficult, and you don't appreciate other people's achievement. So that's one thing. Broad and consistent learning. Consistent learning can make you broader. Being broader makes you appreciate other people's knowledge, so that you communicate well, you live well. That's the social side. But there are also the scientific side. Broad learning can make you easier to find special angles that narrow scholars cannot find. There are many examples. I learned that in recent years that there are many parts of economics that are consistent with evolution. And there are many parts of evolution consistent with new drug discovery. So the third part is pharmaceutical. Okay? The second part is evolution. The first part is economics. A typical example is that we find that if you have if the vertical axis is, the horizontal axis is age, the vertical axis is mortality, you see that human or most mammals have a U shape. They have a very high infant mortality rate, right? Very high infant mortality rate, very high old age mortality rate. They have very low, say, age 20 mortality rate. So why is that? Why is that? Why do you have that U shape? But if it is not mammal, you don't have that shape. You have a increasing mortality rate. Aged bees have a higher mortality rate, but you don't have a high infant mortality rate. So why is that? Evolutionary theory says that you have that shape. You have to have an efficient reason. You have to have an efficient explanation. But the argument is that if mammals is a kind of fact that senior parents transfer energy to their children. That's called mammals, right? You transfer your milk to your children. So it's a transfer fact. So if your growth depends on the fact that senior parents have to transfer energy to the young, then it must be the case that if the child needs to die, he should die early. He should not die at the age of 20 after his or her parents have devoted 20 years of energy. So that kind of a downward transfer from parents to children, if that is a fact, then it must co-evolve with the fact that infant mortality rate is high, because that is the only efficient way. Otherwise, it's a waste. It's a waste of energy to rear the young children. So that's what is that? That's fundamental economics. Efficient way of using energy. And that is also consistent with the pharmaceutical discovery. The new drug discovery has a very high failure rate. It's about 9,999 over 10,000. It's a very high failure rate. So the golden rule of pharmaceutical management is that you have early failure. You want to make your case fail early. That's the fundamental golden rule. Why is that? It's also consistent with evolutionary theory and the economic theory, because you don't want to get a failed case after 10 years of investment. That's inefficient to your company. If it is inefficient to your company, you won't have that company. Evolution in the market will drive you away. So, in any event, I think the previous two examples, both on the scientific side and from Robert Hutchins' general education, would suggest that you have persistent, continuous, and lifetime learning that is benefiting both to your general education, social knowledge, and also to your professional thinking, possibly developing new ideas. The second thing I would like to deliver or share with you is we should try to get used to failure. Okay? I talked to President Wong Qi-hui of Academia Sinica a couple of weeks ago. In economics, he's a chemist, but I'm an economist. In economics, the rejection rate of most professional journals, good professional journals, is more than 95%. So the rejection letter in my drawer is about 10 times more than the acceptance letter. It's always the case. It's always the case. I believe I read a newspaper a week ago. Barack Obama said that he made mistakes every hour, every day. So is the case for scientists. We make mistakes and we get a failure response. Even if you treat us as successful scientists, that's the fact. That's the fact in our background. It's also the case for President Wong Qi-hui, president of the Academia Sinica. He also said that he gets rejection letters all the time. It's also true for Paul Krugman. You know, Paul Krugman, the Nobel Prize in economics, well-known U.S. economist. He said in an open article, published article, he said that he was already the John Bates Clark Award medal. That is the best economist under age 40. He has already got that award, but he wrote that article after he got that award. He said that every time he received a letter from the journal, he had a trembling hand. So even for John Bates Clark Award, making mistakes and getting failure results is a standard measure. So being success is an exception. So keep that in mind. That's two simple points I want to make. Thank you.
I think the message Professor Chu tried to deliver seems to be telling us that along the way to become a scientist, don't become just a well-trained old dog who can play no tricks, right? You should try to learn from the mistakes you make, especially nowadays the interdiscipline research has been becoming more and more important. So broadening the horizon of your knowledge will be very important. Okay. So the next one will be Professor Xu. He's also a former president of National Tsinghua University. Actually, more than 20 years ago, when I was still a student, I started learning astronomy by reading his book, Peaceful Universe. So let's see what he wants to tell us. Let's welcome him.
I have a PowerPoint which I believe the people in the other two rooms can see, but perhaps people here can't see. But anyway, it's not necessary that you have these visual aids. I'm very happy to say that I agree with 100% of what Professor Chu just told you. In fact, the advice I would give you runs along similar lines. That is, never stop being a student. And my personal career, the way I do that is not to be too comfortable. When I get too comfortable in the field that I'm in, I know I'm only doing the safe thing. Okay? So then I switch fields. Right? So I'm much older than Cyrus. I'm 68. I have retired 3 times. This is my 4th job. I'm continuing to carry out this. So let me tell you, I started out in astrophysics, and my words of advice for you are similar to this. I just train broadly in the fundamental sciences. I'm now working on energy. I can tell you there's nobody that's trained in energy. Everybody is an outsider. All right? So to succeed in something like energy or climate change, you have to be trained broadly in the sciences. That means in practice, when you go to college, you should major in physics or chemistry or biology. Those are fundamental sciences. Second, you should always try to understand the problem and find the most appropriate solution. Not you have a solution or you have a technique and you try to fit the problem to your solution or your technique. You're not likely to do important things there. You should understand the problem in a systematic way. You should be bold in your research in energy and conservative in deployment. For the same reason that Professor Chu mentioned. The downstream stuff is very expensive. If you're too free, and I think that's a problem in energy today, people are too fast to deploy and don't spend enough time in doing the research. Make sure that what they have is something really new. You should build on the past, but you should not be bound by it. That is, you should always respect what other people have done before you. But if you just improve a little bit what they've done, that's unlikely to make a difference. You have to understand it so that you don't repeat the same mistake, but not be bound by it. And most importantly, you should follow your interest. You will be good at whatever you do, only if you are passionate or you're interested. That's more important than anything. Whether it's teaching or anything, you have to have enthusiasm for what you do. So in astrophysics, I started out my career working on spiral galaxies. I became quite famous person at a very young age because of my work on spiral galaxies with my professor. And then I realized, I was getting too comfortable, getting too many invited along. So I switched interacting binary stars. Of course, when you do that, you're an old person on a totem pole. But if you work hard at it, you can become one of the top people in the field like this. And then I realized I was too comfortable then, so I switched to working on Saturn's rings. Again, in our case, half dozen people in the world. Stop doing that. We're going to start each time. I was uncomfortable because I had to learn things I didn't know before. It became then very useful in my current work on energy. Finally, I was eager, because it had something to do with planet formation. The first stage was planets form around uniform salt. That's the good thing about astrophysics, is that it's about systems. And energy is about systems. You don't understand the system. Actually, you can not do much that is. The other thing good about astrophysics is it allows you very quickly to make order of magnitude estimates. So you can tell whether what you have is viable or has promise. I'll give you just one example. Okay, suppose we make the following order of magnitude estimate. How much volume of material do you need to power 100 horsepower car? You need. Lots of people like wind. I can tell you, it takes 700 kiloliters per second of wind, typically, to power 700 cubic meters. Does that make sense? Well, how big a volume of cars are you talking about? Probably 2-3 cubic meters. So you need 700 times that in wind, because density of air is much less than the density of a car. Thousands of times less. You don't need it every second, but every few minutes you have to regenerate that energy that's in that car. So it takes you 700 cubic meters of air. How much oil does it take? It takes 9 milliliters of oil. That's why it's so hard to beat wind, to beat any kind of fossil fuel, because chemical energy is millions of times more than mechanical. We measure mechanical energy in joules per kilogram. When we measure chemical energy, it's tens of megajoules per kilogram. That's why it's so hard to beat fossil fuels. You have to realize you want to work. Now if you talk about nuclear, let's say uranium, how much energy do you need to run that power? 0.04 nanoliters. Okay? In other words, in a liter, you can run 1 billion cars. That's ridiculous. Because nuclear energy is millions of times more powerful than any chemical. When you realize that, you realize that much of what we are doing in the world is actually not going anywhere. That's why we're having such a hard time. Because the focus is on the wrong thing. And you say, well, you can't use oil or coal, because even though it's very expensive, we know it gives you a very bad side effect. What is that side effect? We all know. When you burn fossil fuel, you get carbon dioxide. Well, how bad is that? Well, it's greenhouse effect. What's the greenhouse effect? Greenhouse effect, I don't know why there's so much argument. It's so simple. It is simply that the atmosphere traps radiation that comes from the Earth. The Earth is warmed by sunlight, the ground gets warm, and it tries to re-radiate that energy into infrared radiation. There are gases that trap that and prevent it from easily getting out. So the bottom has to be warmer than the top by a certain amount. How much is that? 33 Celsius. That's not bad. Does that make sense? If you leave this room, you go to an airplane, it is 33 degrees Celsius lower. It's below freezing. So that's obviously true. How much of that is due to carbon dioxide? Roughly 27%. So 9 degrees out of 33 is due to carbon dioxide. We know that. Astronomers know that. So that's the cost of the Industrial Revolution. Okay? Because we started burning coal, we then started burning oil, now we're burning natural gas at a very large rate. How much have we burned? Well, at the start of the Industrial Revolution, it's 280 parts per million. All right? Today it's 392 parts per million. So it's a simple calculation. If you get 9 degrees at 280 parts per million, it should be about 12 degrees at 392 parts per million. In other words, it should be 3 degrees hotter over the last 200 years. You may have read in the papers recently, best estimate is only 0.9 degrees, less than 1 degree. So that's all the argument why some people don't believe the models are right. But it's precisely because the theoretical prediction is 3 degrees and not 0.9 degrees that we're in trouble. Why is that? Because I have a glass of ice water, and less energy is coming out the top than the bottom is trying to put out. What happens? Does the temperature rise? No. All of you who learn physics know, as long as you have ice, it stays at 0 degrees. That's what thermostat is. It's kept. Thermostat is like the ice in the world. So we are actually melting ice. That is what we should be focusing on. Not global warming per se. We will get to that 3 degrees or 4 degrees of ice because we continue to add carbon dioxide. But in the meantime, we are living on borrowed time because we're melting the ice in the world. Okay? How much ice are we melting? That's a simple calculation. Right? Roughly speaking, we are adding about 0.58 watts for every square meter. That is, we're radiating less into space than for equilibrium. So you can calculate if at 0.58 watts per meter squared, how long would it take to melt all the ice in the world? The answer sounds comfortably 1,300 years. Okay? But most of us live in the northern hemisphere, and the northern hemisphere only has 10% of the ice. 90% of the ice is in the southern hemisphere. That means if you calculate it, after the northern hemisphere, only 200 years to melt the ice in the northern hemisphere. Okay? If you melt the Greenland ice, the sea level rises by 6 meters. Melt Antarctica goes up 60 meters. How much of Taiwan will be left? Sea rises like that. Very little. Sure, many urban countries where that is a big deal. So the next time you see that polar bear standing on that ice floe, okay, and the ice is shrinking, don't think it's just a bear. That's us. We are living on borrowed time by behaving the way we do because we are melting the ice. And that ice is gone, not only will the sea level rise, many parts of the world won't have fresh water. So it is very serious. The Arctic North Pole ice will be gone in just 40 years. So to reverse this, many people think we have to take down the carbon dioxide from 392 parts per million to about 350 parts per million. So even if we stop tomorrow emitting carbon dioxide, it is not enough. It's going to stay there for thousands of years. We actually have to reduce the amount of carbon dioxide. How long would it take? To put back carbon into the earth at the rate we've been burning it. It took us 100 years to get to this state. It took us another 100 years to get out. So that's the theme that when I started working on energy, I approached that. And I realized that there are only really two basic things, if you don't burn oil, that are either affordable or are big enough in capacity. Of course, sunlight is a lot, but that's very expensive. So the two things are to make biofuels or to go to nuclear energy. Right? So we started doing biofuels. And again, we learned from nature. Why is it that the earth has coal? Why does it have oil? Why does it have natural gas? Very simple. Biomass gets buried, there's no oxygen. If it touches hot rock over tens, hundreds of millions of years, it will become coal. If there is lots of acid around or other things, it will become oil. It becomes too hot, it becomes natural gas. So we want to duplicate this. We have to duplicate in the laboratory. But instead of taking 10 million years to do it, We take 10 minutes. How do we do it? We put something in the atoms of oxygen by putting it into a liquid. That's very hot. Let's say 300 degrees C. But what stays a liquid and is very hot? It has to be very chemically stable. The most chemically stable thing is salt. There's a reaction of acid and a base. If you take salt, like sodium acetate, not sodium chloride, and potassium acetate, it will melt at 235. You melt it at 300 degrees, any flour mass you put in there will quickly become cold. And we've done this, and we think we can do it at very high throughputs. It's because we're using a liquid to transfer energy. It's sort of obvious that this is food. What's the fastest way to cook food? What's fast food? Deep fry it, right? Just deep fry it until it chars. That's what cold is. You can also do similar things and try to make oil very fast, similar to oil or natural gas. And that's what we're working on part of it. The other part is to do nuclear energy. Lots of people, once you say nuclear energy, they don't like it. They say it's not safe, etc. It's not cheap, causes problems. Well, that means I agree with all of them. But that means not that we should give up on nuclear energy. But we should try to make it safer. We should try to make it cheaper. We should make it less proliferation resistant. And it is possible. Again, by using a combination of salt to transfer the heat from nuclear reaction and going away from what is the conventional cycle, which is the uranium-plutonium cycle. Plutonium creates all the problems. And that's to use for. I don't have time to discuss this in detail for you, but you can go on the web. You'll find many, many people talking about thorium molten salt reactors. That's what we're working on. But we're working on it in a very systematic way, because from our work on biofuels, we have a lot of experience now with molten salt. It's probably the most advanced group in the world, I would say, in that technology. So you have to realize what goes on in other fields, see what you can borrow from it. So that's my philosophy.
So Professor Xu's words seem to echo Professor Chu's advice. That is to follow your passion and interest. If you think you are a capable person, then you should try to broaden not only the horizon of not only your knowledge but your contribution to the society. Professor Xu started as an astronomer, and he changed not only the subfield in astronomy, winning the so-called Asian Nobel Prize and the Shaw Prize by his achievement in astronomy. Now, he has almost completely moved on to a completely new field, the research of energy. So the next speaker, I think he has some kind of similar story. Professor Liu, when he was young, he was a radio scientist, and now he is a chairman of the Southeast Asia Regional Center for START. It's an institute research center to coordinate the international global change research for the 10 Southeast Asian countries. So let's hear what you want to say.
Thank you, Professor Wu. The message I want to bring to you today is the following. Everybody's talking about innovation, successful application of techniques, of technology to solve problems. The message I want to bring to you is that many innovations are based on fundamental principles of physics. That's the point I want to bring to you, and I'll give an example of the statement. But before I do that, I would like to echo the message that Minister Chu and explanation Xu mentioned. That is, you should all really learn broadly. That's essentially to train during your school year to learn as broad as possible. And then, when the opportunity comes, you will have the background really to seize the opportunity and really to try to implement what you can do, what you have in mind, with the help of fundamental knowledge. The example I'll give you is essentially an event that happened 5 years ago in Taiwan. In Taiwan, we started a space program about 15 years ago. And 5 years in 2006, 5 years ago, we launched a constellation of 6 microsatellites to monitor the climate and weather of the Earth. And that particular program is called FOLASAT number 3. And that constellation has been so successful that right after its launching in 2006, major weather bureaus in the world, in Europe, in the US, Canada, Japan, as well as in Taiwan, make use of the data we collected by the satellite and improve the forecasting of the weather and also monitoring the climate throughout the world. Especially the data collected by our satellites have proven to be very useful for forecasting the typhoon pattern. And so the operation has been so successful. The next generation of the satellites of the constellation is now being planned by Taiwan in collaboration with agencies in the United States. And we are planning to launch, instead of just 6 satellites, the next generation will be 12 satellites, more satellites, using the same principle to improve the effectiveness of such a constellation. The principle behind these satellites actually is very, very simple, very fundamental. What we use is nothing but the idea of refraction of waves. And everybody knows about Snell's law. What we are using for these satellites, nothing but the Snell's law. I'll explain it to you very briefly. What we have are 6 low Earth orbiting satellites orbiting the Earth at 800 kilometer height. And on each of the satellites, we have a GPS receiver, a very advanced GPS receiver that actually can really locate the satellite location within centimeter to millimeter accuracy. What we are doing now is that on board of each satellite, when it receives signals from the GPS satellite, it locates, determines its position, its location. But when the satellite, this low Earth orbiting satellite, goes behind the Earth, the signal from the GPS satellite will be blocked by the Earth itself. But before that happens, when the satellite goes down, the GPS signal for some time, a period about 10 minutes or so, will be passing through the atmosphere of the Earth before it reaches the satellite. And we all know, law of refraction says, if the signal, the radio wave, passes through a medium that has different refracting index than vacuum, the propagation path will change. This refraction angle depends on the density, the parameters of the medium. Okay, so when the radio wave passes through the atmosphere, during the second move of the sunlight behind the Earth, it measures the refractive index of the atmosphere. If you can determine the angle of refraction. Okay. And if you do that, you get the refracting index of the Earth's atmosphere at different altitudes, because your satellite is settling down. And the ray path goes from the top of the atmosphere to near the Earth. Okay, so that way you actually determine the profile of your refractive index of the atmosphere. And refractive index is dependent on the density, the temperature, the humidity of the atmosphere. So if you have the refractive index profile, you actually can determine the temperature at different heights, the humidity at different heights of the atmosphere. So that essentially measures the temperature from the sky, what we call thermometer in the sky. By launching those 6 satellites orbiting the Earth each day, we can produce more than 2,500 to 3,000 profiles around the Earth for its temperature. This is very important because currently the weather forecasting procedure uses data from weather stations around the globe. There are currently about 900 such weather stations around the globe, and it provides the data every day to the Weather Bureau, and they use them to forecast the weather. 900 of them. And now, with this new technique, each day we can have 2,500 to 3,000 new additional temperature profiles. And that can be used to the weather forecasting models to really improve the capability for weather forecasting. It's not only we have more data, but also the current distribution of data is from the weather stations around the world, which are all located on land. And we know the weather, the atmosphere, actually depends a lot of what's happening in the ocean area. And currently we don't have this information. Now with the constellation that we have, these 2,500 additional points of data actually are distributed throughout the world. So that is why it makes this technique so important and so efficient for improving weather forecasting. And as a matter of fact, it also has proven that with this new data, we can actually predict the direction, the track of typhoon and hurricane much more efficiently, accurately. And because of this success, we are now planning for the next generation of such constellation, 6 satellites, 12 satellites other than 6. And we are also improving our receiver technique so that each receiver on the satellite can receive not only the US GPS satellites, but can also receive new GPS system from Russia and from Europe. So altogether, if after we have successfully launched the 12 satellites, then instead of 2,500 additional points per day, we'll have about 150 additional points because we have more lower up 12 satellites receiving more GPS signals. And with that, I think we can actually improve much better, much more our forecasting, weather forecasting capabilities. And that set of satellites with its orbiting capability, with its global capabilities, the data collected will also be very crucial for our climate monitoring. Okay, so that's essentially this example I want to mention. And the success of such a technique, of such a system, really, as I mentioned, is based on very fundamental physical principles. And that principle can be really implemented for such delicate, such accurate tasks, simply because we now have the technology, engineering to do it. Essentially, we can measure the refractive angle so accurately. Indeed, the way that we measure it is not really measure the angle, but measure the time delay that we receive the signal due to the interaction of the atmosphere. And that time delay, radio signal, we can measure it accurate to 10 to the minus 9. And that is how we make this whole system work. And so the idea is you can really make things work innovatively by using simple principles, but also making use of of the new technology. And that really depends on your own background. If you have a broad background, so that, and also you are not only in fundamental physics or fundamental radio science things, you are also familiar and aware of new engineering, new technology. And the combination of the two essentially would help you to really design, plan, innovative ideas, put them into real world, and some of them would really help our society. And the particular thing that this constellation actually will also help us to understand more about our climate change, understand more about how human society should deal with this problem if we want to have sustainable development. Thank you.
So I should correct one thing I said earlier. I said he was a radio scientist. Actually, he is still a radio scientist. He's actually one of the key leaders to utilize the Taiwanese satellite constellation Formosa 3 to study the atmospheric structure. And that's using a really innovative method that he invented himself in recent years. Okay, so before we move on to the Q&A session, because Professor Chu has some other appointments and he has to leave early, and he said he has some final remarks to make before.
Sorry, this is the first day of the National Science Conference. You can imagine if the first week I will be very busy. I have a dinner appointment. I will be the host. I have to leave. But before I leave, I would like to add a remark, echoing Frank Shu, and a remark contradicting to my previous topic. That is an example of my daughter. I echo Frank Shu that you should follow your interest and passion. That's the most important thing. You will not do something you are not interested in. My daughter is a Harvard master and the second year in the PhD program of Berkeley. And last year, she decided to come back to make cookies and cakes. Okay, that's her passion. That's her interest. So I support her. That's consistent with Frank Shu's ideas. But that's inconsistent with my previous saying that I should kill not her interest. If something is not her interest, it should be stopped earlier. Okay. It's too bad that she devoted in 20 years in learning and then switched track. Sorry about that. Thank you very much.
So, thanks, Professor Chu. And now we are going to take open questions. So, I don't know if the organizer has collected some questions earlier. If not, no? Okay. So, I guess this is now an open session for questions. So, please raise your hand if you have any questions for the academicians here. Okay, yes, please. Do you have a microphone? No? Could you please come here? Yeah. Go ahead, yeah. I think it's better you stay here so that you can see our distinguished guest.
Well, good evening, professors. I'm Celia, and there is a question I would like to ask Professor Liu. As we all know, Formosa 3 has an outstanding ability to gain the rare information of climate from oceans and the polar region. However, the observation will be more accurate in a range over the altitude of 17 kilometers than in the lower atmosphere. Have professors ever encountered the problem of handling the data that are not precise enough? And how can you solve problems?
Yes, indeed. The techniques that we are using are based on some assumptions. And one of the assumptions is that we assume the Earth's atmosphere only varies radially. Essentially, it doesn't really have angular variation. And that actually is one of the fundamental difficulties that we have to try to solve, which indeed that people have devised new algorithms to deal with this. And also, the other problem that our scheme has is the fact that down in the region where from ground up to about 3 kilometers, the refractive index of the atmosphere depends on both the temperature and the humidity. So the data that we collected actually cannot resolve the different contributions from temperature and humidity. And the way that we resolve this is that we make use of modeling results to first fix one of these 2 parameters. For instance, to fix the temperature, and then use our data to find the humidity, and then we iterate this solution, and hopefully it converges. Which I think.
I mean, there is kind of generosity between the contribution of the temperature and the humidity, but we can actually model the already modeled out by the already. Great.
Well, thank you.
All right. Okay. So, any more questions? Okay. Yeah. Three precious occasions, you know.
I want to put a question up for the first speaker. I don't remember the name. I'm sorry.
First speaker?
Okay. He left.
Yeah, sorry. But you can still ask the question. I mean, there's a general question. Yeah.
My question was, he said about economy is working when all of the people are working. But I think the economy is working better if, for example, a researcher makes a very good development and he creates a new technology, something new, different. For example, if it wasn't Leonard Euler, then maybe all the mathematics, well, it was about 200 years ago, or maybe with 50, maybe. So maybe it wasn't computers. For example, maybe it wasn't Alan Turing for the develop the architecture of the computers. Maybe the computers was like 50 years ago, maybe 1 year ago, maybe somebody. But I think the most important for an economy, for the science, for the world is somebody or researchers to create a new thing and a useful thing to change the world. And I don't think the economy is that you need to have a lot of people or human research that is working very hard and I think that's researching. But only a few countries spend a lot of money in researching. For example, in Romania, very few found is spending in researching.
Okay. So you want to make some remarks? I think you can take time to prove you right.
I think economics is a very important field because so much of the world depends on it, right? I would just give an example of its importance to science. You know, Charles Darwin, who invented evolution, the book that he brought with him, he brought 3 books with him onto the, one of them was an economics book, and that was the one that triggered his idea about, you know, what happens when you overpopulate and specimens begin to die. So the key there was to ask crucial questions. Which ones die, which ones survive? That led to the idea of evolution. Not the book that he read about biology or about geology, even though they were helpful. So really to look at it widely, I agree with Professor Chu that it's very good. Sometimes, your best idea may not come from the immediate problem, but from other fields' way of thinking.
And I have an additional thing I want to say about, for example, there are some associations in researching that these teachers, PhD teachers, are not looking to make economics. I mean, they don't want to brevet a solution, a method, and they only just want to say to the world that is a new method, a new research method, and you can use it. And most of the researchers, I mean, in electronics, in device, in engineering, are trying to make some money from that. But I think to change the world and to improve the world to be better, it's more to make a solution that will be free. Because maybe if it's free, maybe other researcher is trying to use your method and develop something better and more better. And I don't think university teachers I saw a few that was looking to economics and they wanted to make profit from that solution, and this is all.
Any more comments about that? So I think the message the academicians try to deliver is that you can always believe in yourself and take your time to prove you're right. Anyway, so that's why we are all gathering here. Not really for the competition. It's actually, for growing yourself up and trying to broaden, as I said, not only just your knowledge, but your contribution to the society in the future. Yes. Okay. Thank you. All right. So, any more questions?
Yes, here.
Okay. Well, we have a lot here. Oh, that's great.
I would like to ask a question to Professor Xu. May I ask that since we are high school students only, and how can we contribute to the field of astronomy? Right? Since you are an astrophysicist.
As high school students, how can you contribute? Or
since the data of astronomy is all free online, and how can we do?
So there's many projects which do use, in fact, amateur astronomers, people with backgrounds no better than yours. The most famous, of course, is comet hunting. Most of the comets are named after not professional astronomers, but by people who have memorized the sky and therefore not confused by bright lights or galaxies, fine comets. Another is to analyze data which relies on pattern recognition. Pattern recognition is something that humans still do much better than machines. So classifying galaxies, for example, in the universe, what their shapes are, the colors are. Right? The human can do that very fast. If you're interested in that, you can find websites which will get you involved in work of that kind. If you really want to do something that's very quantitative, that requires deeper levels of physics or mathematics or chemistry or whatever, then you probably have to wait until at least you're an undergraduate or probably when you're a graduate. Astronomy, the good thing about astronomy is that you don't have to be very deep. You do have to be broad. It's a subject which rewards breadth. It's about the whole universe. So that's a very big place. Very few astronomers. So any particular problem actually has not been explored very deep. So it's possible very quickly to make important contributions. So probably, as a high school student, it would be difficult. Okay.
Okay, thank you. So we have next one. Okay, that's great.
May I ask Professor Shi that how can astronomy researches such as the formation of stars bring us human any actual benefits?
Okay, so I think this is what I was trying to get at. That astronomers, in fact, are obviously immediately least useful of all sciences. But what we bring is knowledge. We build telescopes not to collect heat, but to collect knowledge. Yet, despite that, sometimes accidentally, discoveries in astronomy have great potential impact. For example, all of you have telephone cameras. Those CCDs were developed by astronomers first. The ability for fuel cells, those were developed because the probes that we wanted to send to the planets needed sources of energy, the astronauts. So there are these spin-offs. More importantly, I think it's actually a certain, for myself, where I think I am trying to work on things that have human benefit. It is that exposure to systems. Systems as a whole. We've gotten into trouble on Earth because we haven't thought of the whole system. So typically when we manufacture something, we only think about its immediate end use. We don't think about the energy, the waste that's produced. We have to think about that now. We have to think about things in terms of a cycle, in terms of a system. And that is very good. Astronomy is probably better than that at training people that than any other field, because astronomy is so broad by definition about the whole universe. So all forms of human learning are important to astronomy.
Thanks a lot.
Any more for Adam? Yeah.
As a matter of fact, the techniques I just introduced to you, mentioned to you, is indeed from astronomy. We borrowed from astronomy. This is the so-called occultation technique.
Perhaps I should add one more thing, and that is in the field of education. Astronomy's most valuable contribution to society is that it's very easy to understand. If you look at an astronomical photograph, it's almost like art. The very young children are attracted to astronomy. And, it's a wonderful tool for bringing people into science and technology. That's perhaps our single most important contribution to society, is to breed human power.
I myself is in the field of cosmology, so I would ask this question quite often. I mean, we spend a lot of money doing the research about the size and age of the universe, and what kind of benefit we are going to get from that, right? So when I come across these kind of questions, the most often example I make is more than 300 years ago, when Newton saw the apple falling, and then therefore he invented the gravitation and calculus. So a lot of people, or even scientists, laughed at him at that time. Why bother about the apple falling? Just pick it up and eat it, right? Because the falling time is not going to change, no matter what kind of mathematics you use. But if Newton followed the general thinking at that time, then nowadays we wouldn't have the technology of, for example, transportation, right? Against gravity. So what's going to happen in the long-term future is something you don't know. So what you need to do now is just probably to make the best use of your innovation to satisfy your curiosity, because that's how the human civilization progresses. So, okay. So I think now it's probably about the time to end. So let's thank all the academicians today, and it's really a great honor to have them sit here side by side, sharing their experience and take the young people's questions. Thank you.
那我们有最热烈的掌声，谢谢两位院士，谢谢。Thank you very much. 接下来这就是我们大师对谈的这个活动在此告一段落。那接下来呢，为了欢迎各国参赛代表以及所有的来宾，我们要进入今晚活动的第二阶段，也就是我们的